Hey guys, let's give this thing a shot. Let's turn this upside down for the lectures. I'm going to have to break this into two parts. I tried recording it earlier and it's 15 minutes long, which was too long for YouTube to upload. So we're going to try this in two parts. Go ahead and pause the video right now if you haven't opened up the notes that I emailed you, the types of reactions notes, and restart it once you've got that open so you can look at it or print it off or whatever. Alright, so we're going to start with types of reactions. 5 types of reactions, same types that we learned last year. We're just going to use some slightly different names for them. So if you look at that slide, we've got the synthesis reactions, which are sometimes called combination reactions. Combination reactions makes perfect sense. That name works for that. College professors kind of go back and forth on whether it's called synthesis or combination. The AP test goes back and forth on what they call it. So just know they're both the same thing. Decomposition, combustion, single replacement, and double displacement, which is now going to be called metathesis. Metathesis actually comes from rhetoric, the art of public speaking. When you want to make a point about something, sometimes you'll repeat the same sentence, but you'll switch the order of words just to make the point, to make it stick in people's minds. That's called metathesis. It literally means rearranging the parts. And well, that makes sense for what double displacement is. If you've got two pairs that then swap partners, that's rearranging the parts. So we're going to call that metathesis. It all makes sense. So let's take a closer look at the combination and synthesis reactions first. The basic form is A plus B makes AB. And there's several types that you need to really know very well. First is if any element, especially a nonmetal, is reacting with oxygen or sulfur, it makes the oxide to the sulfide. So the example, carbon plus oxygen makes carbon dioxide. Now we're not going to worry too much about balancing equations right now. You guys know how to balance equations, and for these we're more concerned about predicting the products. So identifying what type of reaction it is, and then figuring out what the products are going to be. So if you see two elements, it's got to be a synthesis or combination reaction. So anything plus oxygen will make that oxide, anything plus sulfur will make the sulfide. The second type is metals with halogens. And again, these are two elements. A metal like sodium with a halogen, group 17, like chlorine, will make sodium chloride. Again, it's just a combination, two elements coming together. Now it gets more complicated if you have compounds doing synthesis, but there's a few patterns here to look at. If you have a metal oxide, it will react with water to make a metal hydroxide. That extra H in the water makes it a hydroxide instead of an oxide. So if you just know those three, well really just two elements coming together, or a metal oxide reacting with water to make a metal hydroxide, you've pretty much got the synthesis reactions down. On to the decompositions. The basic form is the opposite. You have AB splitting up to become two separate pieces, smaller, simpler pieces. And there's several patterns we need to look at here that you need to know. First of all, the opposite of the first combination one is a binary compound decomposing. So water splits into hydrogen and oxygen. If you have two elements, only two elements in a compound, and you decompose it, you're going to end up making those two elements individually. If you have a metal hydroxide, this is the opposite of the last one we just did for the combination, it's going to decompose into a metal oxide and water. So the example, copper hydroxide, when heated, will decompose to copper oxide and water. So the hydroxide, think hydroxide, water, it's all involved in there. The next type are metal carbonates, which will release carbon dioxide and leave behind a metal oxide. They won't leave the metal itself behind. The metal is too active. It's attracting oxygen too well to be left behind all by itself. But you can heat it and release carbon dioxide from that. So if you've got a carbonate, carbon dioxide is what you should be thinking. Metal chlorates, again, will release oxygen, but not the chlorine. The chlorine will stay there. So potassium chlorate will release oxygen to make potassium chloride. Oxyacids then, when you heat those, will decompose to release some non-metal oxide plus water. So the H from the top, from the beginning of the acid, and some O's at the end will make water. And then whatever's left over will be that non-metal oxide. So if it's carbonic acid, in the example H2CO3, carbonic acid, you're going to get carbon dioxide and water. If it's nitric acid, you're going to get water and some nitric oxide, some nitrogen oxide. If it's phosphorus, phosphoric acid, you get water and some phosphorus oxide, usually P4O10. If it's sulfuric acid, you get a sulfur oxide along with the water. So whatever that nonmetal is in the middle, that an oxide of that plus water is how that decomposes. Combustion is reacting with oxygen. So anytime anything reacts with oxygen, it's going to be combustion. Last year, we only talked about hydrocarbons, things with carbon and hydrogen, reacting with oxygen and burning. And in that case, the product was always carbon dioxide and water, because the carbon from the hydrocarbon got all the oxygens it could handle, and the hydrogen got all the oxygens it could handle, so we had carbon dioxide and water. But anything that reacts with oxygen is combustion. In the lab, we did magnesium reacting with oxygen. Technically, that's combustion. It's also a combination, a synthesis. But because it's reacting with oxygen, we end up with a magnesium oxide. We just make the oxide of whatever we're reacting, whatever we're combusting. So anything like phosphorus reacting with oxygen will make a phosphorus oxide. P4O10 is pretty much the standard if you have phosphorus oxide. That's the one that can hold the most oxygens. And the other example is propane, C3H8, reacting with oxygen to again make carbon dioxide and water. The carbon and the hydrogen separate. The oxygen attacks the carbon, and the oxygens attack the hydrogen, to end up with the carbon oxide, in this case carbon dioxide, and hydrogen oxide water. Single replacements, A plus BY, remember the pair shows up, you got the single person showing up to the dance who steals one away, leaving one single. And there's several patterns to these. Metals can replace other metals. And again, we use the activity series. The metal that's more active will replace the less active metal. Magnesium is more active, it's more popular, so it'll replace the iron. Chlorine will leave the iron behind and go to the magnesium, because magnesium is more active, more popular, and so the iron gets left all alone. Active metals, some active metals can replace hydrogen in water. So in that second example, sodium kicks a hydrogen out of water, so the hydrogen bubbles up as its own gas, it's left all alone. And the hydroxide goes with sodium, because sodium is more active, more popular than the hydrogen that started the water. Active metals can also replace hydrogens in acids. So lithium will replace hydrogen in hydrofluoric acid and hydrogen chloride. The lithium's more active, more popular than hydrogen, and the chlorine will leave the hydrogen, go to the lithium, and then the hydrogen's left as H2 all alone to bubble up and go, I don't know, cry from the air or something. Halogens can also participate in this. If you've got chlorine, it'll replace iodine, because chlorine is more active than iodine. And so Ki, the potassium leaves the iodine behind, goes to the chlorine, because chlorine's more active, it's more popular, and iodine is left all alone, and you've got potassium chloride. I'll come to the activity series and a little bit more on this in part 2. This video's already too long. Be right back.